Hello, and thank you for joining this IMechE webinar on hydraulic assessments in the water and wastewater industry. My name is Mark Wilson. I'm an academic in the School of Mechanical Engineering at the University of Leeds, but I'm here today in my capacity as the current chair of the IMechE's Thermofluids group. This is a group of industrial and academic members with interest in all aspects of industrial fluid and thermal systems. Our role includes advising the IMechE in this area and contributing to technical strategy, but our main activity is in developing and delivering lectures, seminars, conferences and events like today to highlight and share developments and capabilities in key industrial applications. If you're interested in finding out more about the Thermofluids group, do please get in touch through the IMechE contacts you've had for this webinar. So I'm very grateful to today's speakers for developing this webinar on behalf of the group. The first speaker, Nick Brown, has worked as a CFD engineer for over 10 years and has extensive experience in a variety of settings. He's been an active member of the Thermofluids group for the last several years, and his industrial input has been very valuable. So Nick leads the computational modelling team at AtomBHR, and he will explain a bit more about the company shortly before he goes on to talk about his computational work. And then complementing the CFD analysis is physical modelling, which our second speaker, Yoav Greenberg, will talk about. Yoav's been a project engineer since 2016, and he has expertise in scaling criteria, which are essential in ensuring that scale models are meaningful. So I hope you find their webinar interesting and useful. It will be recorded and you will receive a copy of the recording after the event. Do please feel free to ask any questions using the Ask a Question box within this presentation interface. This can be done at any time during the talk, and then at the end I will put the questions to the speakers on your behalf. So thank you again for joining us, and I'll now hand over to Nick. Thank you.
Hello and welcome to this webinar on hydraulic assessments in the water and wastewater industry. I'm Nick Brown. I'm the computational modelling team leader from AtomBHR, and I'll be dealing with the computational aspects of the hydraulic assessments, and then I will hand over to my colleague Yoav Greenberg, who will look into the physical modelling aspects. So just to start with a brief introduction of AtomBHR. We started out as BHRA, British Hydromechanics Research Association, which was a government research institute in 1947. This turned into a private consultancy in 1989, and we've been known as BHR Group until very recently. And then, as of last September, we were taken over by Framatome SAS, who are a international leader in nuclear technology. So we, you can see the primary markets at the bottom. We are more aligned now with the nuclear industry, but we still are doing all the other things that we previously did before the takeover. So in terms of what we do, we're a specialist fluid engineering consultancy. We work with our clients with a range of our IP products and research services. As an example, we have a database of sludge rheology, and that's been put into a web-based software called Slot 2.0, which deals with pressure losses in pipe networks for sludge flows. And we deal with a combination of numerical modelling and physical testing, and we use this to validate, optimize and develop products and processes for our clients. As I was saying, primary markets are there below: nuclear process industries, so chemical engineering, oil and gas, and water and wastewater, which is what today's webinar is about. Okay, so water and wastewater, in terms of the treatment, is a very big topic. So this this webinar is really intended just as a taster for what's possible in terms of modelling, how it can be used to make the process more efficient. It's not intended to be comprehensive. If we get enough interest in this webinar, we can look at a more detailed seminar in due course, if that's of interest. So with the increasing world population, drinking water is becoming a much scarcer resource. Also, the more people, there's more waste to process, which basically requires greater efficiency in water treatment, so that we can deal with greater flows, we can use less energy in the process and use less chemicals. In terms of difference between water and wastewater treatment, we look at water treatment as dealing with drinking water, and wastewater as forms of waste such as can be industry, so chemicals. But what I've found that I've more often what I've been dealing with is kind of sewage treatment in terms of the wastewater treatment. So the treatment aims are essentially to treat the water to make it safe for the different purposes. So either for, let's say, drinking water, irrigation, and safe disposal of wastewater into to the rivers and seas. Obviously, for the different purposes, you'll have different measures of quality. So for drinking water, it'll have to be a lot cleaner and a lot safer than just using it in irrigation or disposing wastewater. So I've got a couple of schematics. Water at the top and wastewater at the bottom. These are quite complicated, but I just want to point out a couple of things that we're going to be dealing with going forward. So if you look at the end of the water, you've got a clear water tank, chlorine dosing, so that would be basically like a chlorine contact tank. We've got sedimentation tanks in the water, and which is essentially the same as the clarifiers in so primary clarifier and secondary clarifier in the wastewater schematic. And we've also, so that's what I'll be dealing with. There's a other thing which, in terms of the processes, as I've said, on the left-hand side is the physical process. You've got filters as well, which would tend to look at filtering out larger particles, larger sized particles. So yeah, you've got the chemical, which looked at the chlorine, so that would be the same as ozone, a contact tank. And then you've got a combination in looking at the flocculation tank. I'll not be looking at modelling that in particular, but essentially that you look at dosing a coagulant in order to so that attaches to kind of smaller sized particles, and then that allows them to combine and settle out much more easily than the initial kind of small sized particles. Just a couple of other things to note. So you've got a return sludge pump. So as I was saying, we have a product called Slot, which deals with the pressure losses associated with sludge flow. So whenever you have clarifiers or settling tanks, you're going to have to deal with the sludge that comes out of that. And then if you look at the return sludge, one of the things that we look at is the mixing of return sludge and the primary effluent. So in that process, it needs to be well mixed before it goes into the aeration tank. Okay, so the first kind of case study, or in terms of the modelling that we can do, we'll look at a chlorine contact tank. So that the process is chlorine dosing for disinfection, and what we're looking at is, or the process is looking to achieve a minimum contact time to achieve for the water to be in contact with the chlorine to be disinfected to appropriate safe water quality. So in terms of the modelling, we would carry out a base flow, and then what you're looking at in the video is a transient scalar being modelled. So we implement a kind of pulse signal to start with. So you'd have the initial scalar put at 1, and then after that at 0, and what you can see was that in the video was the propagation of the scalar going through the model, and this what we've in terms of the curve that's been modelled, you see the concentration model at the outlet, and that's how we calculate or determine the residence time distribution. So you can see here we've got different residence time distributions for different numbers of channels, and so what I should say is, in terms of the kind of efficiency of the chlorine contact tank, what you're looking for is to be as close to plug flow as possible, so that you've basically got a consistent velocity throughout. And what you would, in terms of a perfect efficiency, you'd look at basically a really sharp spike in the middle. So basically all of the fluid exiting is exiting with the same age. That's kind of perfect efficiency. So in terms of contact times, we can look at either so-called T5 or T10. So T5 would be the time for 5% of the inlet water to flow through to the outlet. T10 is the 10%. We can look at the plug flow factor, which would be a T10 over torr, where torr is the nominal contact time, which is determined by the flow rate and the volume of water in the tank. And in this case, you would be looking for, so a perfect efficiency would be approaching 1, bad efficiency is 0, and it kind of, in terms of how we would assess it kind of depends, or how I've found it depends what I've been given. It can be, greater than 0.7 or greater than 0.8 is acceptable. Okay, so in terms of mitigation to improve the residence time distribution and improve the contact time, we can look at reducing dead zones and reducing short circuiting. So here we're looking at the underlying flow, velocity contours, and for example, you can see a big dead zone next to the inlet. So what we could look at doing is using flow straightening devices. So for example, an orifice plate. Also, you could look at filling in the bends. And one interesting thing that we found in this study was if you look at the gap, so on the left-hand side and on the right-hand side, so the gap between the baffle and the wall it was found that it's slightly less than the actual channel width was better for the actual plug flow efficiency. Okay, so the next case study, I'm going to look at kind of mixing generally, but with regard to return activated sludge. So I mentioned that in the introduction slide to the water treatment. So this would be in an anoxic zone before looking at putting into an aeration tank. And so you can see on the right-hand side, we've got a pipe for the influence. We've got a couple of pipes for the RAS, the return activated sludge. In terms of modelling aspects, we have an impeller for mixing here. So we can look at a kind of quasi-steady state analysis using the MRF, the multiple reference frame method. In terms of looking at the fluid properties, if the fluid properties in your mixing analysis are so in terms of what you're trying to dose is the same as the bulk fluid, then you can use a scalar. In this case, the RAS has sufficiently different density and viscosity to mean that you need to model it as a multi-component fluid with different fluid properties. Okay, so in terms of assessment, so on the right-hand side, you can see a plot of the mass fraction of the RAS, the concentration, and you can see the red, so that's where the RAS is coming in. You can see the blue, where the influent is coming in. So you can see gradually as it's going through the system, it's getting more consistent to green. Now, in terms of an assessment of mixing, we look at the coefficient of variation, COV. So that's basically the standard deviation of the RAS concentration divided by the mean RAS concentration over a particular surface. So we'd look at a cross-section, perhaps looking at the underflow baffle or at the outlet to see what the COV is there. And for the best mixing, you're looking for as low as possible. So COV of less than 0.05 or 5% is very often used as industry standard for acceptable mixing. Okay, so we can also look at settling tanks. So this process is it's to do with gravitational settling. And in terms of modelling, the kind of things that you need to think about in terms of modelling, you'd need solid-liquid multiphase, so modelling your solid particles. You need to model hindered settling. So this basically accounts for the difference in how particles will settle out due to the interactions when it's more concentrated. And we need to get an accurate idea of the sludge layer. You need to look at the non-Newtonian modelling the properties of concentrated sludge. So just to show on the right-hand side, we've got a picture of a solid concentration contour, and so the flow would come in from the centre at the top. It goes down, and as it's settling out, you get a much higher concentration at the bottom, where the solid sludge will be removed, and the liquor, the fluid, will overflow a weir on the right-hand side. So in terms of an assessment, you're looking at the depth of the sludge layer, and you're looking at the amount of suspended solids in the effluent that's disappearing over the weir, as I talked about. So finally, for the computational modelling, we'll look at pumping station assessment, and what we look at modelling this against the ANSI HI 9.8 design code. A couple of things to point out about this is that I have noticed more and more people, more and more companies asking for a CFD assessment of the pump stations. It should be noted that it is, in the latest version of ANSI, it is still advised that you should use physical models. In particular, computational modelling is not as good as physical modelling in dealing with air entrainment. And at the moment, I would say, and I will show you in a couple of slides' time, the safety modelling can give an impression, give an idea of if there is vortex activity, but it certainly can't give an idea of the specific classification according to the ANSI standard that Yoav is going to talk about a little bit more going forward. In terms of things to think about modelling, one would be, so you can see in this video, we've got water levels at different heights, so which brings about cascades and lots of, so you can see in this case lots of kind of surface turbulence and some air entrainment happening. If you have a case where there are significant changes in water level, then it is required to do a multi-phase to capture the surface interface. And you can basically see that from the pump water levels and the estimated levels throughout the system. If the levels are planned to be the same throughout, then you can basically use a single phase model and just use a fixed surface to model the water level. In terms of how we do an assessment of the pump station analysis, the first thing we'd look at is the swirl angle. So the swirl angle is defined by this theta, the inverse tan of the tangential velocity over the axial velocity at the pump impeller position. So this would be without any actual impeller modelled, but just at the position where it would be. So you can see on the right hand side a plot of the tangential velocity. In this case, you can see it's quite consistent, the tangential velocity acting all in one kind of anti-clockwise direction. So this would result in quite significant swirl. In terms of the ANSI standard, swirl of less than 5 degrees is required, or it's allowed to be up to 7 degrees for infrequent operations, so less than 10% of the time. But if you're looking at a steady state analysis, let's say with a single phase, then you're going to want it to be less than 5 degrees. Flow uniformity, so you can see on the right hand side a contour of velocity at the position of the impeller, and so you can see here there's a small region where there's green, so lower velocity. So in this case you'd have a so essentially you look at the maximum minimum velocity and to compare it to the ANSI criterion and see if it's within 10%. What we can also look at is give an idea of vorticity. So on the right hand side you can see, using the Q and lambda criterion, we can get an idea of subsurface vortices. And in terms of, so the bottom right image is obtained from looking at streamlines. So you can see this kind of tornado-like structure going into the pump valve mouth. So obviously an indication of surface vortices here. We can also look at solid settlement using the so-called shield criterion. So the shield criterion looks at the wall shear stress, and it has kind of critical wall shear stress for different particle sizes. So, for example, if you look in this contour plot on the bottom left-hand side, the blue area, so it's a very low shear stress. So basically, all the particles, any size, will settle out. And then going up towards red, so only particles over a certain size will settle out. So you can see from these contours the idea of which kind of size particles will settle out. Okay, I'll hand over to my colleague Joab now.
Hello, so my name is Joab Greenberg, and I've been at AtomBHR for about 5 years now, and I work in the physical modelling section. So whereas Nick does his CFD modelling, we model the same and similar infrastructure, but building a scaled physical model. So the reason why it's important to undertake modelling is essentially to improve the system efficiency and to reduce cost. Although a physical model can be expensive, in the grand scheme of things, it can make a significant reduction in your TOTEX costs because you will improve your efficiency and reduce the need for maintenance. And just to give an idea, just a typical diagram you can see here about the importance of modelling and to do it early. The earlier you do your modelling, whether that be CFD or a physical model, the cost of the change can be significantly reduced. So for example, if you've already built your station and you get a model of it done, and you determine that you need to dig up all your concrete and relay it or make your hole smaller or bigger, then it's a lot more expensive to do it then than if you'd have done your model before you started digging. So when I'm talking about physical modelling, I'm going to be focusing on pumping stations specifically, but we do model other infrastructure, so things like vortex drop shafts, inlet works, and also things like dams as well. So a wide variety of infrastructure that we can model, but I'm going to focus specifically on pumping stations because that's where a lot of the interesting measurements we take are found. So what are the advantages of a physical as opposed to a CFD or vice versa? So of course, a CFD is substantially cheaper. You're not having to build a large or small model. So you haven't got a long initial build of the model. And if you want to make a big change to your design, it's not so difficult to do. And it's easy to extract data because you've got all the data there in your computer model to take, and you can look back at it later because you can save your files. However, for a physical model, depending on how it's set up, a minor change to design, so for example a baffle in a specific location, can be quicker to test because all you have to do is put in a piece of wood and hold it there and see what it does. And it's easier to test different operating conditions by changing your pumping by adjusting some valves or which pumps you're operating in the model without having to rerun the simulation. And as Nick's also touched upon, things like modelling on vorticity or vortex activity and air entrainment can be more accurate in a physical model than it is in CFD. So when we're scaling a physical model, we obviously don't want to build our design at full scale because our laboratory is not big enough to have a 10-metre tall pumping station. So we want to scale it down. And the scaling criteria we use is a Froude scale model. So we want to maintain equality of the Froude number between the full scale and our model scale when we are scaling it down. And the Froude number is the relationship between the velocity and gravitational effects. The advantage of keeping this the same is that our geometry scales geometrically. So for example, if we have a scale factor of 1 to 7, what in the model is 7 meters will be 1 meter. What in the full scale will be 7 meters will be 1 meter in our model. And that makes water levels much more easy to measure. However, by maintaining the Froude number, other parameters are varied, not necessarily to the same scale factor. So the velocity is actually scaled to the square root of the scale factor, flow rate to the power of 2.5, and Reynolds numbers to the power of 1.5, which means that when we are setting up our test conditions and we're looking at pump flow rates, etc., then it's not just a simple relationship by the scale factor. We actually have to take it to the power of 2.5, which does make a significant difference. The other relationships that we need to look at is the Reynolds number and the Weber number. So the Reynolds number is the relationship between inertial forces and viscosity, inertial effects and viscosity effects, and essentially it defines whether the flow will be turbulent or laminar. As we reduce the scale factor, although Froude number is maintained, our Reynolds number does reduce, and again that's the power of 1.5 to the scale factor. And this is usually the limiting factor to how small we can make a scale model, because we need to ensure that the flow characterization is still turbulent to make sure that we are representative of what will happen in the full scale model. So as we reduce our model size, the Reynolds number will reduce, and once we keep that Reynolds number high enough, usually as per ANSI in the order of about 60,000, so that we are still turbulent in the turbulent regime. The Weber number is also another number which you need to keep higher. We're normally looking for a Weber number of about 120. This is a relationship between velocity and also surface tension. So when we're looking at air entrainment, to make sure that any air bubbles are more accurately modelled, you want to make sure that the Weber number is high enough so that we can more accurately measure air entrainment. So once we've scaled the model, there are various parameters you'd like to look at. So in a pumping station, one of the key things to look at is pump swell. And we measure pump swell using a 4-vane voltometer, which should be in the position of the pump impeller. So you can see in the video here an example of a relatively high pump swell. And you can see that the voltometer is spinning around nice and quick, or not nice and quick as the case may be, because you don't want it to be such a high swell. A high swell is essentially having rotational flow going into the pump. Pumps are designed ideally that the flow is coming in nice and straight when it approaches the impeller. In reality, because of the conditions within the pumping station, it can come at an angle and have rotation going in. If it's coming in rotating in a direction of the impeller, then essentially the flow is already rotating as it hits the pump, and that's going to reduce your pump efficiency. Conversely, if it's rotating against your impeller, that's applying an additional torque onto the shaft, which again is not good for the pump. And of course, if it's varying, you're going to start getting things like vibrations. So a high pump swell can reduce your pump efficiency, it can require increased need for maintenance, it can reduce the pump's operating lifetime, cause vibration, a whole host of issues which can affect your pumps, and ultimately will increase the operating cost of the station if you're having to shut down for repairs, or if your pump lifetime is reduced. Other things you look at is air entrainment, and that's quite easy to see because you can just see the air in the model. We specifically build our models out of perspex so we can see inside and see what's going on. This is quite a severe example of air entrainment, where you've got a free cascade entering into the wet well, quite close to the pump, and you can see the air just being sucked straight into the pump, and you can see in the discharge line the air going straight up into your system. One thing to bear in mind is that because the Weber number isn't maintained, that the air entrainment isn't 100% accurately modelled within your physical model. So you do always need to be extra cautious with regards to air entrainment. In this example here, you can see clearly the air is getting sucked into the pumps. But if the air was not going into the pumps but getting quite close, we would still regard that as being an issue, because we are slightly underestimating air entrainment. The advantage of a physical model is that over CFD is that air is much easier to model in a physical model because you can physically see it there. Whereas to model air entrainment, and especially small bubbles in a CFD model, requires quite a complex multi-phase simulation. And the problem with air entrainment in your system can cause a significant number of issues. So you've got issues of cavitation, vibration in your pumps, and of course as you suck air into the pumps, then you're going to pump that air downstream, which will then cause problems downstream, and you've got to get that air out somehow, somewhere else. Another thing which Nick mentioned earlier is about vortex identification, which, as he stated before, in the CFD model it is quite difficult to identify the severity of a vortex. This diagram here is an extract from the ANSI standard of how we define a vortex in a physical model. So you've got surface vortices which have 6 classifications, from a minus bit of rotation on your liquid surface to a full air core where air is being sucked from the surface directly down into the pump, similar to how you would see if you had, for example, putting a plug on a bathtub, where you see an air core down into the plug hole. And you've also got intermediate levels where you've got a distinct dicole which can enter the pump, or you can have solids being pulled down as well. And you also have subsurface vortices as well, stemming from a wall or the floor, where again you've got 3 classifications, from just general swell and rotation to a distinct dicole, and in the worst case you can actually have air being drawn out of solution from the water and being sucked into the pumps. The vortex is essentially a point or a stream of low pressure. So in the centre of your vortex, your water pressure is much lower due to the increased velocity, and at that low pressure you can either suck air from the surface, or from a subsurface vortex you can significantly reduce your pressure so the air comes out of solution and into the pump, which causes the same issues of cavitation. So this video gives an example of a surface vortex you can see. So this is type 3, and you can see we add dye to the liquid surface, and the vortex just pulls it down the core and goes straight into the bottom of the pump. You can see actually the swirl in this pump is very low because the voltometer is pretty much not moving. However, you can see the vortex is entering the pump. As the dicole or the vortex core hits the pump, you essentially have a point of low pressure, and as each impeller blade passes that point, you can get fatigue on the impeller, it can cause vibration, and again it's going to start causing damage to your pumps. Here's an example of a subsurface vortex then from the floor beneath the pump. First of all, you can see how fast the voltometer is spinning again, so you've got high swell, and your dicole is going straight up into the pump, and again going to cause the same issues as we had before with the surface vortex. Another aspect which we look at is the approach velocities to the pump. So in this example we use an array of pitot tubes to measure the velocity profile at the position of the pump impeller. As I said before, pumps are designed for a nice uniform flow to hit the pump impeller head on. So what this arrangement does is it measures at 9 different points what's the velocity using a pitot tube. Here's an example of one which was measured on a model we undertook a few years ago actually, and you can see that your velocity in line, so as your flow approaches, it's coming at quite a sharp angle round into the pump, and you've got flow separation on the inline in the inlet, which is resulting with a almost 60% reduction in your velocity at one side of the pump. This is going to cause uneven loading onto your impeller, which can cause vibration and damage, wear, which is not too healthy for the pump, and can have a significant impact on your pump's operating lifetime. Normally we're looking for all your velocities to be within around plus or minus 10%. Other factors which we look at are flow velocities to screens using velocity probes. We look at water levels by measuring the water level in the model. We use a manometer tube and a stilling rail to measure the water level more accurately. And just use dye tracing to look at generic flow patterns as well within the model. So just a case study of a model which we've undertaken recently. This is the Prioress Mill. This is a river offtake pumping station where we're extracting water from a river in Prioress Mill, which is in Wales. And the original design had 6 pumps, so 4 large pumps and 2 smaller pumps, with flow coming from the river. The original design has significant issues. You can see in the video we had quite a narrow penstock opening to each of the pair of pump bays, which resulted in a significant drop in water level, which generated air entrainment, and that air was carried towards the pumps. Also, because you had a single penstock for 2 different pumps, you essentially had an asymmetric flow approach to the pump bays, which resulted in significant rotation. So you can see we've got subsurface vorticity, this is at a low level, high swirl, and also surface vortices with the cores going straight into the pump as well, and again a high swirl. So pretty much everything that could be wrong with this model is causing issues. You've got vortices entering the pumps, high swirl, air entrainment. This is going to have a significant impact on your pump operating lifetime and your pump efficiency and the overall cost of running the pumping station. So to reduce these effects, we had to lower the pump forebay so you didn't have such a large drop in your water level going into the pumps. So where you previously had quite a steep slope coming down to the pump bays, that slope was reduced, and we increased the penstock opening sizes, so we had individual penstock openings for each pump bay, which was just significantly larger, so again you don't have that drop in water level. And we put local baffling and benching around the pumps to mitigate against the swirl and the vorticity. That essentially significantly reduced our pump swirl, and it prevented any vortex activity as well. We didn't have such a large drop in the water level going in. These modifications in our model were quite substantial and took quite a few weeks to build, which is why it just shows how important it is to make sure we model things early, because if they'd already built the station and they had to rebuild it out of concrete, then it would have been a much higher cost than just modifying a scale model. So just to conclude, both physical and CFD modelling will identify and resolve many adverse hydraulic effects, whether it be a pumping station or a different infrastructure type. It will negate the risk of a non-standard design, because your model can model whatever design you want, and so you might have a limitation on site, which means you can't use a standard design. And of course, especially early modelling can result in significant improvements in efficiency of your pumps and your infrastructure, which ultimately results in significant cost savings. So if you have any questions, then please submit them, and I'll hand over back to Mark to see if you've got any questions. Thank you very much.
Okay, thank you, Yoav. Thank you, Nick. I hope everyone found that interesting. We do have several questions, and do keep your questions coming in as we answer these questions. You can do that through the Ask a Question box. But we'll start off with a question from Sam Woodhead, going back to the CFD work. How are concentrations most typically modelled in wastewater? As multi-species chemical flows, or can you often simplify the modelling to a single species with generic scalar transport equations?
Okay, thanks for the question. I guess the answer to that is it depends a bit on the process, and it depends on the chemical properties of the fluids that you're analysing. So, for example, we looked at the chlorine contact tank. So, chlorine solution would generally be very close in properties to water, so we can model that as a scalar, as you said, using a single species. If the properties are significantly different, so for example, we looked at the RAS mixing. So in that case, we'd model it as a multi-species. So two different liquids with different properties, density and viscosity, and also depending on the process. So if we think about the settling example. So we actually need to model the solids in that case. So we'd do a solid liquid multi-phase and model the concentration of the solids in that case.
Okay, thank you, Nick. And just as a follow-on to that, again from the same person, Sam Woodhead. What are the kind of meshing challenges in the wastewater industry, and how big can the meshes get in terms of cell count?
Okay, so in a certain respect, the meshing challenges aren't so different to any kind of process or any industrial problem. So we'd be looking at inflation prism layers around the boundaries to refine the flow where the changes happen most next to the boundary. We'd look at refinement near kind of fine detail in the model. And if we think about the pump station model, like for the VOF, you need to model or refine very well the interface between the air and the water, so the water level. In the models we use, there's an automatic process of mesh refinement to do that. I guess specific challenges, if we can relate to the pump station, would be kind of a question of scale and refinement. So it's kind of big models in terms of a number of meters over the whole model, and then you'll need to refine it down. Or have a lot more refined mesh near the pump, where the flow, the changes in flow are much more pronounced in that region, so you need to refine it there. I guess the other kind of challenge related to your question about mesh size is you really want to keep the mesh size as low as is possible. And still keep an accurate solution, and we do that by kind of mesh sensitivity to ensure that the flow kind of parameters are kept the same for the lowest mesh. So to kind of get a bit of a long-winded way to getting to your answer in terms of the kind of mesh count, it would normally be a number of million. So kind of between 1 million and 10 million, something like that, cells.
Thanks, Nick. That also answers another question from Sean Petley about the mesh count on that particular one. So thanks for that. So just continuing with the CFD for a little while before we switch over to the other aspects. So a question from Mark Keating. Using CFD, a single-phase model with fixed upper boundary, for example symmetry, will assume incorrectly that the free surface is flat, won't it? Whereas a single fluid VOF approach would avoid that assumption. Is there anything you could say about that?
Yes, that's correct. But in certain circumstances, you would expect the upper boundary to be flat. So that's essentially, unless the question is kind of thinking about levels between compartments and because of head loss between kind of penstock gates and things like that, and in which case you can estimate the head losses and model the kind of flat boundary in that way. But certainly the VOF model would be more accurate in determining the water level.
Okay, thank you. So next question is from David Odell. Have Framatome generalized or combined results from different wet well pump station models to produce general guidelines of features to avoid or include, to include or avoid in design?
I would say that we haven't done that in a formalized way, but what we do is we assess the pump stations to a standard which has basically done that process already, if that makes sense. So we certainly do compare results of the different pump stations, but essentially we are doing the assessment to the ANSI standard, which basically ensures kind of acceptable performance of the pump station.
What I would add to that is that when we do individual models, they all tend to have their own specific uniqueness and their own challenges and their own specific nuances to the design. We haven't looked at all the design models we've done to compare. However, ANSI and Flight and others produce standards which give a guideline way that wet wells should be laid out with different options for your inlets and your how many pump bays and your flow rates and your levels, etc. However, each individual site has its own challenges, whether that be the choice of pumps or the flow rates or the inlet conditions. And although you can use the standard pump bays, if your approach flow is different, then that would impact on your flow conditions around the pumps and what you see. We've modeled various models in the past which have to the letter followed the ANSI standard or the Flight standard, whichever standard it is, and we've measured it, and you can see they've designed it to that standard bang on, but we find issues which require modifications local to the pumps to fix either a high swirl or vorticity. So even if you do follow the standard designs, there is still potential. So it's such a nuanced thing that a very small effect upstream can impact what happens at your pumps. But there are standard designs out there which can be used as guidelines.
Mm-hmm. Thank you. So I think that partially answers the question from Tony Barber about, is it not possible for new facilities to avoid air entrainment by design? I mean, you've kind of covered some of that in your talk. Is there anything else you want to add to that? You have?
Yeah, I mean, the whole point of the modelling is really to design so that you don't have air entrainment. There are things you can do in your early design stages. So looking at your water levels to make sure you haven't got any significant drops in water levels. So the video I showed in the presentation, the design had quite a large drop in the water level, which is why you had a significant air entrainment. That can be avoided very easily by just raising the water levels. but there are some mechanisms of air entrainment, such as Vorticity, which is not as easy to design out without having done the model first.
Right. Yeah. Thank you. So on to Megan Smith, or Megan Smythe. Apologies, I'm not sure of the pronunciation. Have you ever modelled a biofilter or trickling filter in wastewater treatment? And if so, what were the difficulties with it?
I haven't modelled that specifically, but I have looked at filters before. So the kind of things you would need to look at is you'd model the filter with a porous domain. So you'd have to look at what the kind of specifications were for the filter in terms of the pressure loss for particular flow rate. What else? So biofilter, I guess one thing depends. Do you actually want to model the solids and know how well that is? It's capturing the solids, or are you just kind of interested in the hydrodynamics? So those are the kind of things you would think about.
Right. Yeah. Thank you. So we have about 3 questions left, which I think we can just about manage to do. How do you determine? So this is from Caetano Peng. How do you determine or obtain the fluid properties and the flow losses?
Fluid properties would be a couple of different ways. One, we would first of all ask the customer if they have them. The other case would be essentially sourcing the fluid properties from various standard reference sources, and looking at what the kind of design temperature should be to get those, in particular the density, the viscosity, perhaps what the solids are loading. Is that going to affect the density? Flow losses, essentially you just look at the pressure variation through the system. So look at what the pressure is at the inlet and the outlet, and to see what the difference is. But have you got anything else to add on that, Yoav?
Yeah, I mean, for physical models, we tend to by default use water as our fluid because it's a lot easier and a lot safer to use plain water, and we put in solid simulants to look at solids. And that's normally a good enough approximation of what you get in wastewater. We can use other fluids, but then it gets quite complicated and the safety aspects change as well. With regards to flow losses, we use manometer tubes to measure the liquid levels, or we can use pressure transducers if it's a closed pipe or something like that. We tend to use manometer tubes to measure the liquid level, and because it's level, it's one of the factors which actually scale at the same scale factor. So there's no power difference there as well. So it's one of the easier measurements to take.
Mm-hmm. Thank you. Yeah, and that relates to another question from Stephen Lai. You mentioned the temperature just now, Nick. Is it necessary to consider the temperature effect? And for example, if the tank is underground, there will be a deep sink effect. Is there anything you want to add on that point?
So yeah, temperature definitely affects the properties to start with, as I kind of mentioned. Normally with the kind of water treatment examples, we wouldn't model thermal effects. So it's really just, if you think about thermal effects, I guess, does it have an effect on buoyancy? Does the temperature change across the system? So I guess I'm not entirely sure what the example is, in terms of the underground tank and what effect that would have on any temperature variation across the system. But normally we wouldn't consider temperature effects in those examples.
Okay, yeah. And so we have one last question, which is from David Odell. So another question from David. What kind of efficiency and cost savings can be made? Can any figures be given for a particular example?
Would you like to have a go, Yoav, to start with?
That is the question which we get asked so often, and it's a really hard one to answer. One of the issues we have is that we model something before the infrastructure is being built or wherever they're building it. What then happens is, by the time they commission it 2-3 years, however much later, and they've been running it for so many years, well then they've forgotten all about us, and they don't really. We find it very difficult to get a number of how much has this model saved them. I don't know a number off the top of my head, but from models we've done in the past, thinking of examples, there's one specific model where they were digging a shaft down which was quite deep down and quite wide, and we essentially took a few meters off the diameter and I can't remember the exact depth we basically made, rather than digging a deep wide hole, it was a narrower, shallower hole, which was, I think, possibly tens of thousands of pounds just in digging costs, if not more, just from the model. And then on top of that, we also did other modifications to protect the pumps as well, which would reduce the operating costs and maintenance costs, so your TOTEX is significantly reduced. Another model we had, they'd already, by the time we modelled it, they'd already dug the hole. So they spent all this money to dig a nice big hole for their pumping station. Again, I can't remember off the top of my head what the dimensions were. We modelled it and told them to fill the entire thing with benching. So this big hole that they dug basically got filled in with concrete. So again, for a model which will cost, potentially in the order of tens of thousands of pounds, we can be saving them at least hundreds of thousands of pounds in digging and civils costs. But again, it's really hard to give an exact figure on the costings, because if a station is running for 20-25 years, say, and they're having the efficiency in the pumps has increased, which means your operating costs are reduced. There's less maintenance required, so that's going to reduce other costs of maintenance. But 25 years down the line, we don't really hear back to get an idea of the total cost.
Yes, I was just going to say something about it with the pump operation as well. It's a bit open-ended compared to so what we do is we assess it to make sure that the pumps are going to be operating efficiently. So what's the effect if the pumps kind of wear out and you have to replace them? So yes, it's one of the things to think about.
We also know the modelling also has an impact on other aspects. It's not just cost. So, for example, we could be modelling a station, and if it's going to have horrific sedimentation in there, which means that once a month someone's going to have to go down there with a jet washer and hose it out. Or alternatively, we model it, we minimise that sedimentation or
make it self-cleaning.
Then you got the safety benefits. You're not having to send a man down there every month to go and hose it out. So there's cost, but there's also other aspects which can have a benefit as well. So on safety as well.
That's great. Well, thank you very much, both of you. And I think that's a good point to end. That was our last question. So I would just like to thank everybody for the questions. Thank you for joining us on this webinar. I hope you found it useful. I've certainly learned a lot myself. Thanks for all the questions from everyone, and thank you to both speakers, to Nick and Yoav, for putting this together, and also thank you to the IMechE for running this as well. If you do want to find out more about Thermofluids Group, do please get in touch. We've got an address there on the slide that you can use. So thank you everyone, and that draws this webinar to a close.
Thanks very much.